to the next exciting adventure in mathematics. Here we go. This is lesson, I don't even know, 1.3. Yeah, I knew that. 1.3, transformation of functions and graphs. So we're going to spark your learning by looking at a vegetable. Ooh. So what mathematical observations and questions can you ask? So we notice that each one of these little broccoli thingies is like a spiral. And it almost looks like the same shape over and over and over again as it gets bigger and bigger and bigger in a very certain and regular pattern. So we could ask questions like, what is the formula? How are they related? Each size, how are the sides related? How many are they in each spiral arm? So these are all things that we can kind of sort of start to get at when we learn about transformation of function graphs. So let's do it. Transform some functions, shall we? So check it out. There's two different words that we just used. Transformations. So this refers to any way that a function changes from f of x to g of x. F of x is typically your original function. G of x is typically your new function. So there's transformation, and then there is translation. Not to be confused with those. Transformation, like transformers, includes all of the different ways that you can change a function. Translation is a specific type of transformation where you are moving the graph either up, down, left, or right. And so that's what we're going to talk about. So let's make sure I get all my words right. So transformation, we talked about that one. So different transformations are indicated in a function rule by different parameters. So the parameters are, for example, like this +2, or inside of here -2, things like that. Those are our parameters. Each graph below shows a function f of x in blue. I'm going to write that down because I'm going to forget that 100 times. F of x in blue and g of x in red by transforming f of x in some way, shape, or form. So before we get into this, this is going to be very useful for us throughout this class because these transformations are going to appear into like many different types of functions. So kind of get used to it. This first part is mechanically like how it works, and then there's going to be a chart later on that I will show you that is what you actually have to know and use and manipulate. So just to get us started here, so we've got our f of x in blue, we've got our g of x in red. So notice how we have our original f of x in blue, so that's, let's say this. And so these transformations work on almost any function. So like it doesn't matter what the actual equation of f of x is. All that matters is how is it changing into g of x. Because notice g of x is f of x plus 2. So if we have our f of x right here, and so if you think about every value that we plug in that we can get with f of x, g of x is just going to be 2 spaces higher than f of x because that plus 2 is on the outside. So for example, if we were to input for g -1, and then this is our x values of -1, input for f, so that's right here, -1. Our output for f, just our regular f of x, is -2. That's what is kind of given. And then our output for our g is 2 greater than our f. And you'll notice that we can type in, or we can plug in a bunch of different variables. and they're all going to be two units greater than the original f of x. So when we graph that out, our g of x is right here in blue. Our f of x is just 2 units above that. The exact same function, just translated 2 units up. So when the parameter is on the outside of the f of x, that is our up and down. Okay, and you can think about it, if that's a -2, then your g of x is just going to go down. So on the flip side, what happens if we put a parameter inside of the function? Okay, so again, our f of x is right here in blue. And again, it doesn't matter what the f of x is, it just matters that it's there and it has some values to it. So when we input for g, x equals 1, and then for f, in order to get the same thing, we'd have to change the input for f to be 2 less. So we'd have to do -1. And in that case, we would get our outputs -2, -2. So let's see here. So like x is 1, is that what we did? X is 1. So our output for f is 2. So here, right there. And then our output for f is -2. So I was misreading that. So yeah, so this is our output for f, -2 down here, and our output for g, which is the new function, which is -2 down here, and this is our real function. So you'll notice that it changes a little bit differently. So instead of going up and down, the inputs for the f kind of have to change, and so our graph is going to move along the x-axis. So notice, though, our original function is here. Okay, we put in a -2. We did f of x minus 2, and it moved to the right 2 units. So that might be counterintuitive, but that all has to do with like how the inside mechanics work of the different functions. So basically, so if we're inputting something for f, if we're going to want that to be equal to the g of x, we would have to change the x value essentially before it goes in through the function. So again, I've mentioned this before, I kind of view functions as like computer programs. You take a bunch of numbers, shove it into a function, and then it poops out a result. Well, in this case, you take a bunch of numbers, you change those numbers first, and then you put them in the function, and then it poops out a result. And that's what g of x is. And it's for that reason that it moves horizontally. But this negative sign always gets confusing, so know now that when you're going left and right, you have to, the signs switch. So that's why that negative sign is there. And I'll show it to you in more detail here on the next page. So compare the mapping diagram of graphs of f and g on the top row of the table. Which statement best describes how the inputs and outputs of f and g compare? Let's look at this. How the inputs compare. So the inputs are the same. Each inputs are the same, and for each input, the output of g is 2 more than the output of f. So what effect does the parameter 2 in the rule g of x equals f of x plus 2 have on the graph? It translates the graph when we set up 2 units. So now compare the mapping diagram of f and g in the bottom row of the table. Which statement best describes how the inputs and outputs in f and g compare? So each input for g is 2 more than the corresponding input for f. Yeah, so g is greater than f. And the outputs are the same. Yeah. Woo! And then what effect does the parameter 2 in the rule g of x equals f of x minus 2 have on the graph? So just the 2 by itself translates the graph 2 units to the right. But again, remember it's x minus 2, but that then goes to the right. We talked about transformations, which is the broad umbrella word that we're using. We talked about one type of transformation is a translation, which is the entire graph moving up or down, left or right. Now we're going to look into stretches and compressions. So it's another way that a graph can change. They can either get squished or pulled out, both vertically and horizontally. And so the way we would show that is using our multiplication and our division. But notice how this is multiplication outside of f of x. This is division on the inside of f of x. So just like we had before, things that happen on the outside of f of x changes the y type, the y dynamic, if you will. And then things on the inside of f changes the x, or the inputs that's gonna go into the function. So for our top case here, we've got f of x, which is still in blue, and we have g of x is equal to 2 times f of x. So everything that you have with f of x is just going to be twice as greater, right? So then you'll notice that like our minimums, maximum, minimum, maximum is multiplied by 2. So 2 here turns into 4. Negative 2 here turns into negative 4. And so you have a vertical stretch. That's what we call that, a vertical stretch. Now, if this 2 were like a 1/2 or any number less than 1 and not negative, then you would have a vertical compression. It would squeeze smaller. So in the same way here, this number, the parameter, again, this is, in this case, the parameter is 2, and it's 1/2, is a vertical stretch. And so, again, it changes the input. So, like, if you were to input into g -2, the input for f of x would be half of that, because it would be -2 multiplied by 1/2. So the inputs would change for the functions, and the outputs would still be the same. So let's go through some of our whatever. Compare the mapping diagram and graphs of f and g in the top row of the table. Which statement best describes how the inputs and outputs of f and g compare? So we talked about it. For this top row, the inputs are the same. The outputs are going to be different, and that is basically our x values are going to be the same, but our y values are going to change. So inputs are the same, and for the given input, the output of g is 2 times the output of f. So what effect does the parameter 2 in the rule g of x equals 2 f of x have on the graph? It stretches the graph vertically by a factor of 2. And that's how you would say that. It stretches the graph vertically by a factor of 2. Compare for the bottom row. Which statement best describes how the inputs and outputs of f and g compare? So as we mentioned before, in our bottom row, the inputs end up changing. So like, let's say if I said x equals -2, for the f of x, it would be 1/2. It would be half of that, and then for g of x, it would just be -2. So the inputs end up changing, and the outputs stay the same. So right there. So what effect is the parameter 2? So again, we're referring to just this 2. I know it looks like 1/2, and it is 1/2, but in this case, the parameter is this number underneath the 1. So then on the flip side, if this whole number was like 3 instead of 1 over 3, it would be a compression as opposed to a stretch. And again, we will see some of that in just a moment. So finally, our last different type of transformation is a reflection. The reflection of function graphs. And that is by throwing a negative sign in there, you can reflect it either around the x or the y axis. So let's see if some of this is starting to make sense. So thus far, when we did things on the outside of a function, that affected our graph vertically, right? So when we added something outside of f of x, it moved it up or down. When we multiplied something outside of f of x, that stretched it either taller or shorter or squished it. So if we throw a negative sign around f of x, what is that going to do? So I told you it's going to reflect the graph. How is it going to reflect it? If you thought to yourself vertically, then you are right. So a negative sign on the outside of f of x is just going to flip the graph around, or I guess around, or flip it or reflect it with respect to the x-axis. So again, here's our blue function. We throw a negative sign on the outside of that, and then it just flips it around the x-axis. So now this is the mirror image of our function. And again, our inputs are going to be the same. Our outputs are going to be different by a factor of -1. So it's just going to change the sign. So likewise, if we throw a -1 inside of the function, we are then changing the input that is being thrown into the function. Thus, it is reflecting it around the y-axis. So it has horizontal movement, similar to what we've been seeing over and over again. And as you've been seeing over and over again, the rest of this should be pretty self-explanatory. Compare the mapping diagram for the top one, which statements best describe the inputs and outputs. So the inputs are still going to be the same, and the outputs are going to be opposite because there's a -1. So what effect does the parameter of -1 have? So it reflects the graph around the x-axis. So again, on the outside of the function, it makes the graph move up and down. So if it's flipping, it's going to flip up or down. The bottom row of the table, which statement best describes how the inputs and outputs of f and g compare? So the input of g is the opposite of the corresponding input of f, and the outputs are going to be the same. Again, that's the same that we've been seeing over and over again. The inputs change because we threw a negative sign inside of the function as opposed to outside of the function. And it reflects it around the y-axis. So this is where I always get screwed up. I'm really bad at even and odd functions. But here's the definition. So an even function, quote unquote, is a function that where if you take f of -x, it is going to equal f of x. And an odd function is going to be f of -x is equal to -f of x. And so, do they show us graphs? No, they don't. But later on, I got messed up with trig functions in this, but you would use this to figure out whether it was even or odd. I think we'll see some examples later on. As you can imagine, what happens if we do a whole bunch of different stuff all in the same function? So yes, this is getting progressively more and more difficult. So here we go. They have so graciously given us this wonderful little chart. So this is what the lesson is all about. So if you have g of x and you have an f of x, these are the different types of parameters that you can have up here. So notice, I mentioned earlier, when you go on the inside of f, it's 1 over b. So remember that b is always on the bottom there. A and k are on the outsides. So remember, a is a a vertical stretch or compression. K is a translation, up or down. And then everything on the inside here deals with horizontal stuff. And notice that there's a negative sign here. And it tells you what all of them are right there. It also says things like if A is greater than 1, then it's a stretch. If A is in between 0 and 1, then it's a vertical compression by a factor of A. And then if there's a negative there, it adds a reflection across the x-axis. So this is a really, really great chart to have. So what I did, and this is what I highly encourage you to do, if you can do it on your iPads, is I took a screenshot of it so I can pull it up. When I start doing some of these examples, I can have it on the screen while I go through some of these things. So let's try some out. Describe how to transform the graph of f of x shown to obtain the graph of g of x equals negative f of 2 of x minus 3 quantities, whatever, and then minus 1 on the outside, and show the graph. So I believe this is f of x. So we need to do all of these things to show it. Let's see. Do they actually give us a picture? They will eventually. So let's just take it one step at a time, okay? So we've got, if we zoom in on this a little bit, so we've got a couple of things going on. We've got a negative, we've got a 2 inside of the function, and then we have an x minus a number, and then outside of the function we have another thing right there. So if we were to look at this, let's pull up this guy right here. So at the top here, it gives us our generic parameters, and we can use this to label all of our letters, and then this will make the rest of the problem really easy. This is a problem you're going to see over and over again, like find the parameters, graph it, don't graph it, write a function based on the graph, things like that. So let's just go left to right. That's what I like to do. So our first parameter is a. It's on the outside of the function. In this case, if we look at that, there's no number there, but it is an insinuated -1. So we can say a equals -1. Our next number is on the inside of the function. It's a 2, but notice right here, our parameter is supposed to be 1 over a number. So if we were to make our 2 1 over a number, what would that look like? So our b is going to be 1 over 2. Does that make sense? So think about it. So if we do some algebra here, 1 over b equals 2. Okay, so then we're going to multiply both sides by b and divide by 2. So then b is going to be equal to 1/2. So don't let this part confuse you. Make sure you're watching for that. Okay. Let's see here. What's next? Okay, inside we've got x minus 3. That's going to be our x minus h. So there's a minus sign here. There's a minus sign here. So our h is actually going to be positive. So you always switch the sign, or if you just remember that there's a negative sign here, that's going to then switch your signs. Either one works. However it makes the most sense in your brain. So then we have this last one on the outside of our function. That is going to be our k. So in this case, our k is going to be a -1. So each one of these represents a different transformation. And we can use this chart to easily figure it all out. So let's see here. Match the parameter to their effects. So, okay, we're going to get rid of my face. So a equals -1 is a reflection across the x-axis. And I can either just know that off the top of my head, or I look a, -a, where a is greater than 0, adds a reflection across the x-axis. B is 1/2. B is in between 0 and 1, horizontal compression by a factor of b. So this is going to be a horizontal compression by a factor of 1/2. H is equal to 3. H is greater than 0. Horizontal translation, write H units. Bam. And then last but not least, K is -1. A vertical translation, down 1 units. All that hard work and effort paid off. Yay. Why is the value of b equal to 1/2 and not 2? So again, that's kind of what I was trying to share with you. This 1 over b in the generic function is a 1 over b, so you want to make sure that it changes and, oops, and that's why we need that 1 over 2. So why is h positive but k is negative when the function has minus signs where both parameters show? So again, we kind of talked about that. There's a negative sign in there that we need. So apply these transformations to a few reference points on the graph of f of x. Remember, b and h affect functions' inputs, and a and k affect its outputs. For a point x and y on the graph of f of x, the image of the graph of g of x is this. So basically what they're saying is, if you imagine and you kind of think through what all of these different things would do to their reference points, so notice they give us some reference points here. So you can apply these transformations to each one of these reference points. And then you can come up with new reference points. So let's see here. For our reference point, so what they did here, bx plus h, ay plus k. So then that equals, we added in some of our a, b, h, and k stuff. 1/2 x plus 3. So then we can just take this -2, shove it into 1/2 x plus 3. So that's going to be -1 plus 3, which is 2. Boop. And then we plug 0 in. It's going to have a 3 in the x-axis, or in the x spot. Then we add 3 in there. That's going to be some weird, crazy number. We'll go with that one. So now we have those 3 reference points. We can make a graph. So what they did is they just took those 3 reference points, plotted them, connected them, and then voila. But you can see, so first it reflected this whole thing around the x-axis. And then what did it do? Then it compressed it. It squished it a little bit. It stretched it. And then it moved it down. So sometimes that's hard to visualize. That's why we use reference points. Okay, let's try this out. So we're going to model with transformations. We've got a real-world situation, kind of. So Matias is driving at a constant speed from his home to Fairview for the weekend, as shown. How can we use transformations of the graph of the distance Matias has driven from home as a function of time to obtain the graph of the distance that remains to Fairview. So that's a really convoluted thing to like say and use, but whatever. You gotta start somewhere, I guess. But so the car driving a distance at a constant speed. So our total distance is 220 miles. Our speed is 55 miles per hour, and looks like Fairview is 132 miles that way. Okay. So write a model for the distance d of n Mattia has driven from his home as a function of time. So distance, we have a speed and we have a time. So our distance would be equal to our speed times our time, right? So in physics, we call it velocity because there would be a direction, but we don't necessarily really have a direction. Anyway, so his speed is a constant speed of 55 miles per hour. We're going to multiply that by time in hours, and that would give us our distance. So that's what we got right here. But notice they restricted the time to 0 to 4. So number one, you can't have a negative number. It doesn't make sense. And at 4 hours, he's made it. So you're not going to drive longer than that. So if we graph the model, it's going to look like a straight line. So this is the time that he drives. This is the distance. It's going to look just like that. Woo. Y is domain restricted. We talked about at that point he arrives at his destination. He would not keep driving. That would not make sense. So write a model for the distance dr remaining to Fairview. So the closer he gets to Fairview, the less distance he has to go, right? So it's going to be a similar thing, but you just take the total distance, which is 220, and you're just going to subtract the amount that he has already driven, which we have already figured out is 55t. So there is, I guess, our new function. Where they say, how is this model found? Okay, we just talked about that. The expression for dr of t includes the expression dh of t. Write dr of t as a transformation of dh of t. So what we got? Dr of t, and then dh, which is, yeah, dh is how far he's traveled. So you can say dr is just, so originally we said 220 minus the amount that he's traveled. Well, we can also rearrange that and just say negative of the amount that he's traveled plus 220, which makes it a little bit more recognizable in our transformation world of functions. So here we've got a -1 right there. So our a is going to be a -1. There's no numbers on the inside. So because there's still a t there, all of those numbers are insinuated to be 1. So since they're all multiplied together on the inside there, I'm sorry, I guess since b is multiplied together on the inside there, b would be an insinuated 1. H is a minus h, but that's not there at all either. But since it's not multiplied by anything, it would be an h minus 0. Or I'm sorry, the 0, h would be equal to 0. And then k would be 220. So then if we apply all those transformations, we would then get a graph that looks like this. So again, it's kind of a far-fetched stretch of a real-world example, but you kind of start to get the point.